Bismillah ar-Rahman ar-Rahim. This is an information theory problem. We have two discrete random variables, A and B, and we are interested in the maximum mutual information between A and B. A takes the values from A1 to AN with these probabilities, and B takes the values from B1 to BM with these probabilities. The conditional probabilities, the probability that random variable B is equal to Bj, given that the random variable A is equal to AI, this probability is denoted by eta Ji, and these are given. We cannot control these conditional probabilities. The mutual information is given by this double sum. It is generally the double sum of the joint probability log 2, then the joint probability divided by the product of the marginals. These two probabilities can be written in terms of the probability of B given A. And this joint probability can be written as the probability of B given A times the probability of A. Hence, the mutual information can be written as the double sum over I and J, eta Ji, those are the conditional probabilities, times the probability that A is equal to AI. And inside the logarithm, we have in the numerator eta Ji. In the denominator, we have this term here, the probability of B, that the random variable B is equal to Bj. Now let's define I, A sub k, and B. So here, we are replacing the random variable A by one of its possible values, which is A sub k. We are defining this quantity as a single sum, and this is a sum J from 1 to M, eta Ji. So again, this is the probability that the random variable B is equal to Bj, given that random variable A is equal to AK. Log 2, and then in the numerator, we have also the conditional probability divided by the probability that random variable B is equal to Bj. If we define those quantities, we can write down the mutual information between random variables A and B as a sum I from 1 to N of those quantities. Each one of them is multiplied by this term here, which is the probability that random variable A is equal to AI. Suppose that we have obtained the distribution or the probability mass function of random variable A that maximizes the mutual information. Let's call the maximum mutual information C, C for capacity. We want to prove the following result. If we use the probability mass function of A that maximizes the mutual information, then all those quantities, I, small ak, and B, this is the same. This quantity is equal to C for every k from 1 to big N. Again, what we are interested in, that for the PMF that achieves the maximum mutual information, those quantities will not depend on the index k. They will not depend on the specific value that random variable A takes. All those quantities will be equal to the maximum mutual information C. Let's do a proof by contradiction. We will assume that those quantities are not all equal. And we will show that in this case, if there is a BMF of A for which those quantities are not equal, this BMF cannot be the BMF that maximizes the mutual information between A and B. Without loss of generality, let's assume that the maximizing PMF is this distribution, and the summation, which is the mutual information between the random variables A and B, is equal to C. But let's assume, to challenge this claim, let's assume that those quantities, I, small a1 and b, is distinct from I, small a2 and b. Specifically, we will assume that if we use a1, then we get a result here that is strictly greater than C. If we use a2, then we get a result that is strictly less than C. If all those quantities are above C, then we can multiply by the probabilities, and then we sum. Then this summation here, which is equal to C, will be strictly greater than C times the sum of the probabilities, which is 1. So we get that C is greater than C, which is impossible. Again, and I think this is intuitive, if one of those terms is above C, and without loss of generality, assuming that it is I, small a sub 1, and B is above C, then there must be another term that is less than C. And without loss of generality, let's say that it is I of small a sub 2 and B. The idea of the proof by contradiction is to come up with a different probability mass function for the random variable A that will increase the mutual information, thereby contradicting the claim that this PMF maximizes the mutual information. We will use now a PMF which is defined in this way. We will take the probability that random variable big A is equal to A1, and we will increase it a bit. We add big delta. We will take the probability that the random variable big A is equal to A2, and we will decrease this probability by delta. Delta is a positive number, and we choose delta to be strictly less than the probability that random variable A is equal to A2, so that this difference here is still positive. For the other probabilities, we will keep them as is. So we have the BMF of random variable A that is claimed to maximize the mutual information. This is the probability that random variable A is equal to small a1, and then small a2, and then small a3, and so on. We will work with a new PMF. In that PMF, the probabilities will be kept the same except these two probabilities. Now, we will make the probability that random variable A is equal to A1. We will make this probability here, I will denote it by bar. It is equal to the original probability plus a delta. And for the probability that random variable big A is equal to small a2, we will make this probability denoted by B bar A2. It's the original probability, but now minus delta. This one is increased a bit. This one is decreased a bit. The sum of the new probabilities is equal to 1. We have a valid BMF. And note, of course, that if we change the BMF of random variable A, the BMF of random variable B will change, because the probability that random variable B is equal to Bj by the law of total probability is the probability that random variable A is equal to AI times the conditional probability, which here eta ij. So this is the probability that random variable B is equal to Bj, given that random variable A is equal to AI, and then we do a summation I from 1 to n. Now we are changing the A probability, so those probabilities will also change, as we will see. To show that there is a contradiction, we will show that there is a delta, there is a positive delta, that will actually make the mutual information higher than the claimed maximum. And that's a contradiction. And if we reach that contradiction, this means that this assumption that we have here is false. And indeed, all those quantities are equal. This is the idea. We will take this difference and we will try to show that there is a choice for big delta such that this difference is strictly positive, indicating that we are able to increase the mutual information above its claimed maximum. We will write down the definition of each mutual information. The difference is that here we use the new PMF, and here we use the PMF that is claimed to be the maximizer of the mutual information. So just write down the expression of the mutual information. Now we will split this logarithm into two terms and this logarithm into two terms. So from here I can take this and write it as log 2 of eta ji plus log 2 1 over the probability that random variable B is equal to Bj using the new PMF. And we will do the same here. We will write down this logarithm as the logarithm to the base 2 of eta ji plus log to the base 2 1 over the probability that random variable B is equal to Bj. Here we use the old BMF, or the BMF that is claimed to maximize the mutual information. We do the split. So now rather than having two terms, we have four terms. Here, this product is simply the joint probability A is equal to AI and B is equal to Bj. We can rewrite the joint probability as the probability of A given B times the probability of B. And those probabilities, regardless of whether they are old or new, we can just do the summation over I here and there, and we get a result that is equal to 1, because we are summing a BMF. Yes, it is the conditional BMF, but there is no A except in this probability, and so the summation with respect to index I will give us 1 here and 1 there. So these two terms now can be written as terms only with a single sum with the index J. We are summing over the possible values taken by the random variable B. So this is what we will do to these two double sums. Now, what about those two guys? Note that these terms are the same, are common between the double sums. And what we have here is a summation using the new PMF, and here a summation using the old PMF. Now, if the random variable A is equal to A3 or A4 all the way to AN, these two probabilities are exactly the same. All those terms will cancel out. The only two survivors is when I is equal to 1. In this case, if I is equal to 1, then this probability is equal to BA of A1 plus delta. So we end up with delta, and then multiplied by summation j from 1 to m, eta j1 log eta j1 to the base 2. If I is equal to 2, then this probability becomes the probability of A2 minus delta. But here we have the probability of A2. So the surviving term will be minus delta, and then the summation j from 1 to m, eta j2 log eta j2 to the base 2. Again, in these two double sums, we now use our constructed PMF. For all values of I except 1 and 2, the terms here and there are the same. When I is equal to 1, we have a probability here that is the probability there plus delta. And when I is equal to 2, the probability here is like the probability here, but with minus delta. This difference becomes delta times this bracket. Our next step is that we will divide here by the probability that random variable B is equal to Bj, and we will do the same here. And of course, these guys are not in this expression, so we will have to have minus delta and then this bracket to compensate for the terms that we have added. What is the purpose? Why did we do this? So that this summation here is exactly the definition of I, small a1 and b, and this is I of small a2 and b. So this is the idea. And we know that this difference by assumption is positive because this is assumed to be greater than c, and this is assumed to be less than c. So now this becomes delta times a strictly positive quantity. Now we take this here and rewrite it as a double sum. This is like opposite to the step that we have done earlier. We took the difference between these two double sums and wrote it as delta times a bracket in which we have a difference between single sums. Now we will do the opposite step. We will take this delta times the difference between single sums and we rewrite it as a difference between two double sums. In the first double sum, we have the new PMF, and here we have the PMF that is claimed to be the optimal in the sense of maximizing the mutual information. Note that, again, this is equal to this because those probabilities are exactly the same if I is 3 or 4 all the way to big N, but if I is equal to 1, then this probability is higher than this probability by delta, and if I is equal to 2, then this probability is less than this probability by delta. So we take this, rewrite it as the difference between these two double sums, and then we repeat the step that we did above, which is to take this joint probability and write it as a probability of A given B times the probability of B. Now we are summing the conditional PMF of A, no problem. This will give us 1 here and 1 there, and we are left with just the summation with the index J here and there. When we do this, this single sum here is exactly like this one. This one has a minus sign in front of it, and this one has a plus sign. So these two guys canceled. And now our situation is the following. The difference of the mutual information using the new PMF and the old PMF, this difference is exactly equal to delta times the difference between these two quantities assumed to be strictly positive. And now the surviving terms will be this sum here and this sum here. We can combine these two guys as summation J from 1 to M, and then the probability that random variable B is equal to Bj using the new PMF, and then the logarithm to the base 2. Let's now study this term here. What is the difference between the probability that random variable B is equal to Bj under the new PMF and the old PMF? Well, the probability that random variable B is equal to Bj is the probability that random variable A is equal to AI times the conditional probability that B is equal to Bj given that A is equal to AI. Those guys do not change. So we have these two sums, and by the way we have constructed the new PMF, when the index I is equal to 3 or more, then these probabilities are exactly the same. If I is equal to 1, then this is equal to this plus delta, and if I is equal to 2, then this probability is this probability with I equal to 2 but minus delta. And so when we take the difference is delta, and then between brackets we have eta J1 minus eta J2. This is the difference between these probabilities. What about the ratio which appears in our expression? In the numerator, subtract and add the probability that B is equal to Bj using the old PMF. And now what we have is the difference, and the difference is given by this quantity divided by the probability that B is equal to Bj. Here it is. Okay, so the difference is delta times this bracket, and we divide by this probability, and then this divided by this is 1. The difference between the mutual information is this term here plus this summation, and now we know that this ratio that we have inside the logarithm is equal to 1 plus delta over the probability that B is equal to Bj using the old PMF, and between brackets we have eta J1 minus eta J2. In our investigation till now, we haven't employed any inequality. Basically, all the expressions are exact. And now it's time to employ an inequality for any positive alpha. The natural logarithm of alpha is upper bounded by alpha minus 1, and we have equality if and only if alpha is equal to 1. Now, if we have a real number that is strictly positive, then the reciprocal of the real number is also strictly positive, which means that we can rewrite down this inequality by replacing alpha on the right and left hand sides by 1 over alpha. If this inequality is true for any positive real number, it must be the case that len 1 over alpha is also less than or equal to 1 over alpha minus 1. Len 1 over alpha can be written as minus len alpha. So minus len alpha is less than or equal to 1 over alpha minus 1. Now multiply both sides of this inequality by minus 1. Because we multiply by a negative number, so the inequality is reversed, and we have len alpha greater than or equal to 1 minus 1 over alpha. Let's go back to the logarithm that we have in our expression. This is the logarithm. We can write down log to the base 2 as the natural logarithm divided by the natural logarithm of 2. And now our inequality tells us that we can take the natural logarithm of this quantity and lower bound by 1 minus 1 over what we have inside the logarithm. So this will be 1 minus, here we have 1 over this. So what we get here is 1 plus this term here. 1 goes with 1, and what we have is minus delta over len 2, and then eta J1 minus eta J2. The difference in the mutual information is greater than or equal to delta, and then this positive quantity by assumption. Then what we have after employing the logarithm inequality is minus 1 over len 2, and then delta divided by this probability times this bracket here. And then we have this probability. I can write down this probability as this term here, plus the probability that random variable B is equal to Bj. Here, I mean using the old PMF. So this is the probability, the new probability that B is equal to Bj, and this is what we get when we employ our inequality here. This probability goes with this probability, and we will have a term minus big delta over len 2, and then we have summation eta J1 minus summation eta J2. Now this is equal to 0, because each sum is equal to 1. because we are here summing the probability that B is equal to Bj, given that A is equal to A1. And here we are summing the probability that B is equal to Bj, given that random variable A is equal to A2. We are summing PMFs. Each one gives unity, and the difference is 0. So the surviving term is minus 1 over ln 2, and then we have delta times delta, that's delta squared, and then we have this bracket times another copy of itself, so that's eta g1 minus eta g2 squared, and let's not forget this guy here in the denominator. It's a positive probability. So this now is equal to 0. We have a lower bound on this difference. What is this? This is the mutual information that is claimed to be the maximum mutual information given some PMF for the discrete random variable big A. What we did is that we perturbed the PMF. We took the probability that random variable big A is equal to A1. We increased this probability by delta. And we took the probability that random variable big A is equal to A2, and we decreased this probability by delta. We have constructed a new PMF, the mutual information using this new PMF minus the mutual information that is supposed to be the maximum. This difference is lower bounded by the following: delta times this positive quantity minus delta squared times this summation. And here we are summing positive quantities. Note that even if this summation is equal to 0, then this mutual information is greater than this mutual information. If this summation is positive, the claim is that there is a delta that can make the new mutual information minus this mutual information strictly positive, which means that this mutual information is not really the maximum, and the PMF is not really the PMF that maximizes the mutual information. Can we make this term strictly positive? Yes. Take delta as a common factor. What do we have inside? If we take delta as a common factor, we'll have this difference, I A1 and B minus I of A2 and B minus, and then we have this summation over ln 2. Let's call this thing phi. Then we have minus phi delta, and we have delta. Delta is positive. Can we make this bracket positive? Yes, we can make it positive, greater than 0, if we choose delta to be less than this difference here divided by phi. There is a positive delta that can be chosen. It must be less than this quantity so that we make the lower bound on this difference strictly positive. And of course, it must be less than this probability, because the new PMF has the probability that random variable big A is equal to A2 with this quantity minus delta. We want this guy minus delta to be strictly positive. We can choose a delta that is less than the minimum of these two guys, and if we do so, we have this mutual information greater than this one, thereby contradicting the claim that the PMF BA is what maximizes the mutual information, with the assumption that those quantities are not the same. One of them is greater than C, and the other one is less than C. Now, if you maximize the mutual information, that's it. You cannot find a mutual information that is higher. Our conclusion is that the PMF that maximizes the mutual information between discrete random variables A and B must make all those quantities equal to each other and equal to the value of the maximum mutual information. The solution we have just finished is elementary. We can reach the same conclusion using the KKT conditions. Here is the mutual information between A and B. Let's now write this mutual information as psi of B. So that's a function of vector B, the vector that contains the PMF of random variable A. We can rewrite the expression of the mutual information as this double sum, and then the probability that is equal to AI, here it is written as PI, and then we have, those are the conditional probabilities, those are given, and we cannot control them or change them. And this is the probability that the random variable B is equal to Bj by the law of total probability. This is summation V from 1 to n, the probability that random variable A is equal to small av multiplied by the conditional probability that B is equal to Bj, given that random variable is equal to av. We can solve the problem of maximizing this mutual information given the constraint on vector B that the sum of its elements is equal to 1. May the sum be k from 1 to n, this is equal to 1. And let's ignore the non-negativity constraints. This problem is a convex optimization problem for which the KKT conditions are necessary and sufficient for optimality. The reason for this is that we have an affine constraint, and we are maximizing a concave function, which is equivalent to minimizing a convex function. So let's start by verifying that this function is indeed concave in the vector P. Let's just check it using the definition of a concave function for every P and Q. So Q is another vector that contains a PMF, so non-negative entries that sum to 1. And for a function psi to be concave, we need to show that psi of lambda p plus 1 minus lambda q, where lambda is between 0 and 1, this is greater than or equal to the convex combination lambda of psi of p plus 1 minus lambda psi of q. We can show that this right-hand side minus the left-hand side is a non-positive quantity. So we write down psi of b, psi of q, and then psi of this convex combination of p and q. And these are these two lines. To proceed, we split this double sum into two double sums. In one of them, we have lambda pi, eta gi, and then the logarithm. In the other, we have 1 minus lambda qi, eta gi, and the logarithm. the sums that are multiplied by lambda can be combined. We have here pi eta gi, pi eta gi, and then the logarithm. When we combine these two guys, eta gi goes with eta gi because we have this minus sign here, and then this summation comes to the numerator and is divided by this summation here. We handle the sums multiplied by 1 minus lambda similarly. We then employ our inequality that for a positive real number alpha, len alpha is less than or equal to alpha minus 1, we change the logarithm to the base 2 to len this quantity divided by len 2. And then we have the upper bound is this quantity here, minus 1. And we do the same here. Let's multiply first by this minus 1. Here we have these two guys together are the joint PMF of random variables A and B. So this double sum is exactly equal to 1. Now, if we consider this, note that this summation is exactly the summation that we have in the denominator. This summation is the probability that random variable B is equal to small b sub j. So these two guys go together, and we are left with the summation with index j, and then the summation that we have here in the numerator. Now, if you look at these sums, here we have lambda, we can take it outside, and then we have again the joint probability of A and B. This double sum applied to these two guys will give us 1 times lambda, so we get lambda. The same here, we have a PMF. This is the probability that random variable A is equal to small a sub v, and then this is the probability that random variable B is equal to small b sub j, given that random variable A is equal to small a sub v. These two guys together are the joint probability, and when we apply the double sum, that's 1, and we end up with this 1 minus lambda. So the double sum applied to this quantity here will give us lambda plus 1 minus lambda, and this is 1, and we have minus 1 from here, that's 0. This means that the upper bound is exactly equal to 0, and the same applies here. We have shown that this quantity is non-positive. This means that psi applied to the convex combination of vectors p and q is greater than or equal to lambda psi p plus 1 minus lambda psi q. That's exactly the definition of a concave function. Our optimization problem is to maximize the mutual information, which is now represented by this concave psi of p. We are minimizing a convex function, and we have this constraint, which is affine. We have a convex optimization problem for which the KKT conditions are necessary and sufficient. Let's now write down the stationarity KKT conditions. We will write the Lagrangian, which is the negative of this function, plus lambda, that's the dual variable or Lagrange multiplier. And then we have our constraint. The stationarity condition means that the partial derivatives of the Lagrangian with respect to the components of vector b, all those partial derivatives must be 0. Write down epsilon b explicitly. Now we need to differentiate with respect to pk, and k is 1, 2, all the way to big N. Let's start by differentiating this term here. If we differentiate with respect to pk, then we pick lambda, which is the Lagrange multiplier. And then here we have a p, and here we have it also. So let's apply the product rule. Let's treat those as constants and differentiate with respect to pk here. When we do so, we end up with a single sum. And what we are summing is eta jk. We have k here because we are partially differentiating with respect to pk. And then we have the logarithm. Again, I is equal to k. We are not done yet because the p probabilities are living downstairs here. So now we need to differentiate this logarithm, keeping this guy as constant. So plus 1 over len 2, and then we have the double sum pi eta gi. We need to differentiate this logarithm with respect to pk. So this will give us 1 over this summation. And then this summation, it includes the term pk times eta jk. By the chain rule, we will get this term here. Let's see what we have. This summation is exactly the quantity I of small ak and b. What about here? As we did above, when we checked the concavity of function psi, these two sums are the same. They can be eliminated, and we end up with the summation of eta jk. Eta jk is a PMF. It's the conditional PMF of random variable b, given that a is equal to small a sub k. When we do the sum over j, we get 1, and we end up with just a constant. The stationarity conditions yield equations. In those equations, this quantity of interest is equal to a constant. K does not appear anywhere else. This quantity is indeed the same, regardless of the value of k. This is another solution to our problem using the KKT conditions.